Pick two prime numbers. Let us take 5 and 7. Now I am going to ask two questions that have no obvious reason to be connected. First question. In the world of remainders after dividing by 7, is 5 a perfect square? That is, can you find some whole number whose square, reduced by throwing away 7s, leaves exactly 5? The squares mod 7 are 1, 2, and 4. 5 is not among them, so the answer is no. Second question. With the primes swapped. In the world of remainders after dividing by 5, is 7 a perfect square? 7 leaves a remainder of 2, and the squares mod 5 are just 1 and 4. 2 is not one of them, so again, the answer is no. Two questions, two different worlds, and both came back no. They agreed. Now try 3 and 7 instead. Is 3 a square mod 7? No. Is 7 a square mod 3? 7 leaves remainder 1, and 1 is a square, so this time, yes. The answers disagreed. Here is the strange fact this whole video is about. Whether those two answers match, or flip, is decided by a hidden symmetry between the primes. And you can see that symmetry as a picture, a grid of dots, cut by a single diagonal line. Let us slow down and name what we are looking at. Working mod 7 means we only keep track of remainders after dividing by 7, so the only numbers that exist are 0 through 6. In that small world you can still square things. 1 squared is 1, 2 squared is 4, 3 squared is 9, which is 2 after removing a 7. Keep going and the non-zero squares that appear are exactly 1, 2, and 4, 3 of them. The numbers you can reach, 1, 2, and 4, are called the quadratic residues mod 7. The ones you cannot reach, 3, 5, and 6, are the non-residues. And notice the count is even. For any odd prime, exactly half of the non-zero remainders are squares, and half are not. For 7, that is 3 and 3. To keep the bookkeeping tidy, mathematicians write this with a single symbol, the Legendre symbol. It takes a number and a prime, and it returns just +1 if the number is a square in that world, -1 if it is not, and 0 if the prime divides the number. +1 for yes, -1 for no. That is the entire vocabulary we need. So each pair of odd primes gives two of these plus or minus 1 answers. Is the first a square in the second's world, and is the second a square in the first's? You might expect no relationship at all between them. Instead, there is an exact law, and it is one of the most celebrated results in all of mathematics. It says the two answers are the same, unless both primes leave a remainder of 3 when divided by 4. And in that single case, the two answers are opposite. Written as a product, it is even sharper. Multiply the two Legendre symbols together, and the result is -1 raised to a power. The power is half of 1 prime minus 1, times half of the other prime minus 1. If that power is even, the product is +1, and the answers match. If it is odd, the product is -1, and they flip. Carl Friedrich Gauss found the first complete proof of this in 1796, when he was 19. He was so taken with it that he called it the Golden Theorem, and over his life he returned to it again and again, publishing at least 6 different proofs. Today, hundreds are known. We are going to follow one of the most beautiful, due to Eisenstein, that proves the whole thing by counting dots. Before the proof, let us pin down exactly what we are trying to explain, with real numbers. Back to 5 and 7. We already saw that 5 is not a square mod 7, so its Legendre symbol is -1. And 7, which is 2 mod 5, is not a square mod 5 either, so that symbol is also -1. 2 minus 1s. Their product is +1. The answers matched, and the law agrees. 5 leaves remainder 1 after dividing by 4, so the exceptional both are 3 case does not apply. Now the disagreeing pair, 3 and 7. 3 is not a square mod 7, giving -1. But 7 is 1 mod 3, and 1 is a square, so that symbol is +1. A -1 times a +1 is -1. The answers flipped. And sure enough, 3 and 7 both leave remainder 3 after dividing by 4, exactly the case the law flags. So the entire content of the theorem is that sign, +1 or -1. Our job is to explain, without ever computing another remainder, why that sign comes out exactly the way it does. The explanation starts by turning one of these symbols into a counting problem. Here is the bridge from squares to counting, and it is called Gauss's lemma. Take the symbol for 7 as a square mod 5. Look at the multiples of 7. 7 times 1, 7 times 2, and so on. But only up to half of 5, so just the first two multiples. Reduce each one mod 5, but keep the remainder in the range that can also go negative. That is, if a remainder lands above 2.5, count it as a negative amount instead. What Gauss's lemma says is that the Legendre symbol equals -1 raised to the number of times you had to flip a sign. Let us just do it. 7 times 1 is 7, which is 2 mod 5. 2 is below the halfway mark, so no flip. 7 times 2 is 14, which is 4 mod 5. 4 is above the halfway mark, so that is 1 flip. 1 flip total. -1 to the first power is -1. And indeed 7 is not a square mod 5. The lemma turned a question about squares into a tally of how many products spilled over the halfway line. Counting spillovers is progress, because spillovers are something we can draw. But there is an even cleaner count hiding underneath, and finding it is the key step. Counting how many products spill over the halfway line is awkward. It turns out there is an equivalent count that is far easier to picture. For each multiple, instead of asking whether it spilled over, ask a different question. How many whole multiples of 5 fit inside it? That is the floor, the round down of 7 times the number divided by 5. And the remarkable fact is that the number of spillovers and the total of all these round downs always have the same parity. They are both even or both odd. So for deciding a sign which only cares about even versus odd, you can use whichever you like. So the sign we want is -1 raised to a sum of round downs. The round down of 7 over 5 plus the round down of 14 over 5, and so on. One term for each number up to half of 5. For 5 and 7, that sum is 1 plus 2, which is 3, an odd number, so the sign is -1. Same answer as before, reached by adding up round downs. Now, the round down of 7 times something over 5 is secretly a geometric quantity. It counts lattice points underneath a line. And that is the doorway to the picture that proves everything. Here is the picture. Draw a grid of dots. Along the bottom, put one dot column for each number from 1 up to half of 5. Since 5 is small, that is just 2 columns. Up the side, put one row for each number from 1 up to half of 7, which is 3 rows. Every place a column meets a row, place a dot. 2 columns times 3 rows makes 6 dots, arranged in a neat rectangle. These 6 dots are the whole game. The number of them, 2 times 3, is exactly half of 5 minus 1 times half of 7 minus 1, which you may recognize as the very exponent in Gauss's golden theorem. The mysterious power in the formula is nothing more than the number of dots in this little rectangle. So if we can split these 6 dots into 2 groups, and show that one group counts the round downs for 7 mod 5, and the other group counts the round downs for 5 mod 7, then the two halves of the theorem will be sitting in the same picture at the same time. To split them, we draw one line. Draw the straight line from the bottom left corner that rises with slope 7 over 5, the line where 5 times the height equals 7 times the distance across. The first thing to check is that this diagonal never lands on a dot. A dot would sit on the line only if 5 times its height equaled 7 times its position across. But 5 and 7 are different primes, with no common factor, and the coordinates are too small to reach a shared multiple. So every one of the 6 dots is strictly on one side of the line or the other. None are stranded on it. That is exactly where the proof uses that the 2 primes are distinct. Now the diagonal has carved the rectangle into 2 triangles. Below the line sits a lower group of dots. Above the line sits an upper group. Count them. 3 dots below, 3 dots above. 3 plus 3 is 6, the whole rectangle, with nothing missed and nothing counted twice. Everything now depends on what those 2 triangles are secretly counting. Look at the dots below the diagonal, column by column. In the first column, the line has risen to a height of 1 2/5, so only the dot at height 1 sits below it, that is 1 dot. In the second column, the line has risen to 2 4/5, so the dots at heights 1 and 2 are below it, 2 dots. 1 plus 2 is 3, but 1 and 2 are exactly the round downs we computed earlier, the round down of 7/5 and of 14/5. The lower triangle is literally counting the sum of round downs for 7 mod 5. Now do the upper triangle the same way, but reading by rows instead of columns, which is the same as swapping the roles of 5 and 7. Row by row, the dots above the line count the round downs of 5 times the height, over 7. That sum is 0 plus 1 plus 2, which is 3, and by the identical Gauss lemma argument, that sum controls whether 5 is a square mod 7. So the two triangles are not just two piles of dots. The lower one is the exponent for 7 mod 5, and the upper one is the exponent for 5 mod 7. Two Legendre symbols, living in one rectangle, on opposite sides of one line. Now watch it close. The lower triangle counts the exponent for one symbol. The upper triangle counts the exponent for the other. Add the two triangles together, and you get every dot in the rectangle. No more, no less, because the diagonal missed them all. So the two exponents added equal the total number of dots, and the total number of dots was half of 1 prime minus 1 times half of the other minus 1. Now multiply the two Legendre symbols. Each is minus 1 raised to its triangle's count, so their product is minus 1 raised to the sum of the two counts, which is minus 1 raised to the total number of dots, and that total is precisely the exponent in Gauss's theorem. The product of the two symbols is minus 1 raised to half of 1 prime minus 1 times half of the other minus 1. That is quadratic reciprocity, and we proved it by refusing to let a rectangle of dots be counted two different ways. No manipulation of remainders. Just two triangles fill a rectangle. The picture also tells you, at a glance, when the two answers flip. The product is minus 1 exactly when the number of dots is odd. And a rectangle has an odd number of dots only when both of its sides are odd. The two sides are half of each prime minus 1. Half of a prime minus 1 is odd precisely when the prime leaves a remainder of 3 after dividing by 4. So the sign flips exactly when both primes are 3 mod 4, which is the clause in the theorem we started with, now visible as a fact about whether a rectangle has odd sides. Watch it happen. For 5 and 7, the rectangle is 2 by 3, one even side, so an even number of dots, so the answers agree, both minus 1 as we found. But swap the 5 for a 3. Now the rectangle is 1 by 3, both sides odd, 3 dots, an odd count. The product is minus 1, and the two answers must disagree. That is exactly the flip we saw at the very beginning. 3 not a square mod 7, while 7 is a square mod 3. Change 1 prime, change the parity of a side, and the whole relationship turns over. The symmetry was a shape all along. Step back and see what carried the argument. We never factored anything, and after Gauss's lemma, we never touched a remainder again. The entire proof was a single refusal. A rectangle of dots must hold the same number whether you count it by the triangle below a diagonal or the triangle above. One count is the first Legendre symbol, the other is the second, and the diagonal keeps them apart because two distinct primes never let a dot land on the line. Symmetry between the primes became symmetry of a picture. There are two loose companions worth naming, proved the same counting way. Whether minus 1 is a square mod a prime depends only on the prime mod 4. Whether 2 is a square depends only on the prime mod 8. Together with the golden theorem, those three facts let you compute any Legendre symbol quickly, without ever hunting for a square. Gauss proved his golden theorem 6 different ways and left more behind. Today there are hundreds. This one, Eisenstein's, from 1844, is the one that makes the strangeness ordinary. The deep link between any two primes is not deep at all, once you draw the right rectangle and the one line that splits it. A power became a count became a triangle of dots, and two triangles, filling one rectangle, proved a symmetry that runs through the whole of number theory.